Okay, hey everybody. So today we are continuing with NLP, and today we're going to hit two main things. One, word vectors, and actually more specifically, word embedding. So word vectors is kind of like the umbrella term for any numerical representation of words. And yesterday we talked about bag of words methods. So count vectorizer and TF-IDF were the two pre-processing methods that we talked about yesterday. Today we're going to talk about one more, and that is using word embeddings. And I'll talk about that later. Other thing we're going to talk about today, and this is going to be really, really quick, just like show you all how to implement it, is topic modeling. So topic modeling is the soft clustering method that is most used for NLP if you ever wanted to cluster your NLP data. And what's really cool about topic modeling is, I'll give you all a quick preview. Topic modeling kind of spits out a visualization, or you have the ability to spit out a visualization like this to visualize what your group of text data is talking about. So in this case, similar to clustering, I chose 4 clusters, but it's kind of interactive and you can sort of see like, all right, are there different things that are being said in each cluster? I'll get more into this in a little bit. But before we start, I've linked to a PDF slide deck. It's created by another instructor. I like using this specific slide deck because I used to not have one. But I'm going to go over this slide deck to just give a quick, gentle introduction to what word embeddings are. Okay, so word embeddings are a newer way to represent text. And it is really powerful because where bag of words methods, we talked about that yesterday, we lose the structure of sentences and text and we lose, tone. It's really just focusing on the occurrence of words. Now, word embeddings keep all of that. So word embeddings embed meaning into the vectorization process into your vectorization process. Cool. So let's think about what meaning is. Kind of meta, but meaning is the idea that's represented by text. Sure, that is when you're reading something that's written out, what is being conveyed. Meaning can also be conveyed through words, through verbal speech. And as you know, the way that you speak might be quite different from how things are written out. More specifically, in like different kinds of text, you might have different styles of how sentence structures are put together, semantics, choice of vocabulary, so on and so forth. To get even more abstract, meaning can also be the idea that is expressed in a work of writing or art, and meaning doesn't have to be represented using like dictionary definitions of words. If you think about things like sarcasm or actually, yeah, that's like I think that's like the most common example. Like when you say something, but you don't mean the words that you're actually saying, and your tone might convey something completely different. So how can a computer interpret language? So yesterday we talked about this over here. We talked about count vectorizer and TF-IDF, where there's actually no notion of similarity of meaning of individual words. So yesterday we talked about a satire versus non-satire article. And within those articles, I think a lot of them were political. So within politics, there are a lot of like subtopics. You can think about that. So maybe in some articles, they were talking about elections, and in some articles, perhaps they were talking about specific legislation. And those you can say are like two subtopics of politics, whether it's satire or not. Now, in TF-IDF, there is very little notion of similarity between words used in the realm of legislation and words used in the realm of, elections. So features like that could be important, right? One way that you can go about this is maybe you build like a word count to say, all right, if I'm counting any sort of like legislature kind of related words, add a word count to that, maybe feature engineer something like that, have another one for feature engineering a count of election related words, but that's a very, very manual process. So that's one of the downsides with count vectorizer and TF-IDF. No notion of similarity or meaning of individual words. And they're only giving the context of importance in a corpus. So as we saw with word counts, it's really just the occurrence of words. And with TF-IDF, yes, we've kind of extracted a little bit more meaning using TF-IDF because a word that is more unique to a specific line of text might be seen as more important or informative. But that's kind of like where we cap out. So for example, texts that are talking about Plaza Hotel and texts that talk about Waldorf Astoria should have a high similarity, but this is not exactly captured in TF-IDF or count vectorizer as vectorization methods. Another way that computers interpret language, and we're way past this as well, is through synonyms and like just dictionary definitions. So if we know that there's like a dictionary that maps the connection between words, we can potentially use that, but we don't really use that anymore because it's very, very manual. And can you imagine having to compare similarity in text using a whole dictionary of synonyms? That can be very, very intense. So only true in certain sentence contexts. So that's one big drawback. For example, proficient is listed as a synonym for good, but good doesn't always have to mean proficient. You know, depending on the context, synonyms don't always work out. Synonyms can also be subjective. That's kind of related to what I just said. And also it's hard to update new words and slang, as well as it's a manual upkeep of a thesaurus, because you're literally mapping all of these words to each other. We don't even use this method anymore. Even once we've gotten to like count vectorizer and TF-IDF, we use that a little bit less. Cool. So this brings us on to word embeddings. So word embeddings are representing words based on context. So this is one way, or actually this is the way that word embeddings are trained and created. So it's based off of the notion of distributional semantics, which is the phrase that says that a word's meaning is given by the words that frequently appear around it. So it's not as straightforward as like, all right, what is the meaning of banking? I look up the dictionary definition for banking. There it is. You'll see that because there are so many unique words that occur in life and in the world and in different languages as well, it's a lot more efficient to build a word's meaning based on a distribution of words that appear together with said word. So when a word appears in a document, its context is the set of words that appear nearby. And if you're generating your own word embeddings, which is actually a lab in Canvas, I'll point you all to that later, you can create their meaning by fixing a window around that word. So let's just say we want to create some word embedding for the word banking. And so for every occurrence of the word banking in our training data, we're going to get these context words of plus and minus 5 words from the word banking. So from here, what is banking characterized by? Government debt problems, crises, 2009, that was a big banking crisis. Europe has banks, there's regulation. India also has banks, so on and so forth. So with many, like hundreds and thousands, millions of examples of the word banking being used, you can sort of train the machine to learn what banking means, not directly, but what banking can mean with its given context. And so how word embeddings are created is they're usually trained on very large groups of text. So one example of word embedding is actually trained on like almost the entirety of Wikipedia in like the year 2014. And based on just doing this for every unique word or a lot of unique words, you're creating word embeddings for all of these words. Any questions about this so far? Okay, so it's pretty abstract. So after going through all of this training, and this training is actually using a neural network process, and you'll see in the process of creating your own word embeddings, it uses a neural network as well. Oh shoot, what was I gonna say? Oh, right. So because of that, most of the time, this can be a very intense process. We usually use pre-trained word embeddings, and I'm actually going to be using one of those in a little bit when we go back to our notebook. But yeah, cool. Oh, also, when you have your word embeddings, each word will be represented by a vector. And how long that vector is depends on your library or what word embeddings that you are using. But one pro of that is that every word will be represented by the same number of features. So we'll see an example of that later as well. Cool. So one common example of using word embeddings is through the library word2vec. So we're actually going to see an example of word2vec later. It literally stands for word to vector. So what it does is it uses a neural network to compute some vector representation for each word using this process. It captures the meaning of the word in a corpus using predefined windows of words. And then there's also two different ways to do this. I'll show you all a diagram. This is not the most important thing, but there are two different ways to do it. And as I was talking about previously, there are readily available pre-trained embeddings on different corpora, such as Wikipedia. Like I was talking about, they literally trained word embeddings for like hundreds and thousands of words off of Wikipedia, and Google News. There are also some pretty commonly used word embedding pre-trained word embeddings on Twitter as well. Cool. So two different ways to train the neural network. I know we haven't gotten to neural networks first, so this might not make a lot of sense, but you can imagine that this is continuous bag of words, which is one way that word embeddings are trained. So given some input words, and let's just say the sentence is pineapples are spiky and yellow. If that is the sentence and we want to figure out the meaning of the word spiky, we're going to take the input, and this is with a window of 2. So the 2 words before it and the 2 words after it. So you're going to input these words. Some computation is going to go over here, and the model is going to learn that, okay, when I see these words, you're probably talking about spiky. Skipgram is the next part to it. Is, all right, given an input word spiky, what is the meaning of spiky? This is a small example, but in a larger example at a larger scale, this output would have a lot more words that define its context. This process, not the most important thing for right now at all. Cool. So with word embeddings, how do we know that word embeddings are useful? So this is using a library that's pre-trained. I think this is the one that's pre-trained on Twitter data. And you can sort of see, and this is basically plotting the word embeddings in 2D. So each of these words, you can see that, for example, the word slow, and let me just mark it over here. The word slow has this coordinate over here, -0.3, +0.3. This is basically a PCA representation. So usually word embeddings are roughly between anywhere from 50 to 500 dimensions, and it depends on what library you're using. You can you can pick how long you want your word embeddings to be. Usually the more features there are, the more detail you get. So anyways, this is a PCA representation of all of these word embeddings. And what you notice is that in plotting superlatives, you can see that there are patterns that arise in plotting superlatives. So from going from slow to slower, there's this kind of relationship, which is a similar relationship as going from short to shorter. Same over here. So going from the root form to the ER form has a pretty similar pattern across all words. And then going to the EST word, you can see it's a similar pattern for a bunch of different words. And the fact that even in 2 dimensions, lowering this down to 2 dimensions, you see that pattern means that the word embeddings are capturing some sort of meaning within these words. Any questions about interpreting something like this? Okay, so another example is company to CEO that I have over here. The great thing about word embeddings is your words don't have to be dictionary words anymore. As long as they exist in your training data enough, you can actually create a word embedding for it. So I believe this one was trained on either, I want to say it's either Twitter data or Wikipedia data, which is why, because of that, it's able to map these proper nouns. And proper nouns are not even something that dictionaries have to this extent. So this has the ability to map company to CEO, is able to map this relationship, which is really cool. So for example, I actually don't know any of these people, but you can get the Chrysler CEO to this person, Walmart CEO to Macmillan, so on and so forth. And the fact that they all have a similar trajectory, that means that the relationship between the entities are similar. And it is, because these are company to CEO relationships. Cool. Any questions before? Yeah.
What's the labels for the X and Y axes?
So the X and Y axes are actually just principal components. So this is literally just PC1 and this is PC2. So these numbers, and we'll see a few examples of word embeddings in a little bit. All those numbers or the features don't really have any inherent meaning. It's when put together, they have relative meaning to each other. And I think it'll be a little clearer when we see some examples when we get to the notebook.
Thank you.
But yeah, but these are principal components. Cool.
Thank you.
Any other questions? All right, let's get into this notebook then. Like I was saying, I said this before the recording, I believe. I'm on Google Colab because I broke my local environment again. On Google Colab, the code works on, and if you have Python 3.7 or below, all of this code should work on your local environment, and all the code that's on the repo should also work in your Jupyter notebook. And if it doesn't, let me know. Cool. So new things that we're going to use, we're actually going to use PCA so that we can plot some of these later. But what we're going to do is we're going to use the library GenSim to look at some word vectors. There are actually two main libraries that you can do word embeddings with. So GenSim is one of them, and I'll show you all the differences when we get to it. And another one is Spacey. Most people, I actually recommend that you use the Spacey library. So I'll show you all what that is later. But GenSim, I think it's easier to see what like word embeddings are all about. Okay, I'm not going to rerun this cell, but first what you got to do is you got to load in the word vectors. So there are a lot of pre-trained vectors that GenSim has. So you can kind of like look through it and pick one. So from here, these are all the, let me just double check. Okay, yeah, so this is the one. So models, these are all of the pre-trained word vectors that are available, and you can actually see what they are trained on. So the one that I'm using is GloveWiki GigaWord 100. So GloveWiki GigaWord 100 is this one over here. They have 400,000 tokens, I believe. No, 400,000 vectors. That means you can have word vectors for 400,000 different words preloaded in here. It is trained on Wikipedia in 2014, and it was trained on 6 billion tokens. There are a bunch of others. You can see that this one was trained on Twitter. This is on Google News. This one's on Russian data, which is cool. And yeah, there's a bunch of others. So from here, that's what I'm loading. This one takes a little bit of time to run. So I actually ran this before the study group. And once you've got the word vectors, you can actually treat the word vectors like a dictionary and just look up words. So I looked up the word coffee, and coffee actually has this word vector. Oh, something else to note is that this vector has a length of 100. And that's because this is, which is the one that I had. So this is the one, usually you can tell how long it will be based on the ending of the name. So all of them end with some number, usually like 50 to 500. So yeah, this one is 100. So these 100 numbers are just some numerical representation of the word coffee learned from Wikipedia in 2014. You can pretty much look up a bunch of different words. So for example, if I want to look up not just coffee, if I want to look up the word data, data has a word vector. Not every word is in here. As you saw that there are 400,000 word vectors, but if you have like a super random word, like something like that, it's going to tell you that it's not in vocabulary, which makes sense because if it has to store word vectors, it can't store every single random word that exists. So we have some simple words. Coffee exists. So these numbers currently inherently doesn't really mean anything to us, but the importance of word vectors is the relative similarity to other words. Some of the functionality that you can do within GenSim is you can actually look at similar words. So if I'm looking at, and let me zoom in, I know this is pretty small. If I'm looking at the most similar words to the word coffee, immediately it gives me all of these words. And these are all mostly like drinks, or I guess there are a couple examples of like food, things that you would have with coffee. I don't know what corn comes in, maybe corn, I don't know, corn syrup, or maybe the word corn just happens to appear a lot in conjunction with the word coffee in a lot of contexts. So yeah, looking at most similar. So you have the word and the similarity value, which goes from -1 to 1. Again, it also works for proper nouns. So looking up the word Hilton, with Hilton, you can see that you get hotel because Hilton Hotel. You get other hotels, which is cool. You get Vegas. I guess there's Hilton in Vegas, I assume. You get all of these like hotel related things. So other things that you can do, this most similar method also does like negative similarity. So what's really cool is, all right, let's look and see what is like a woman king and not a man. And I think this is pretty cool. If you put the result of this, it's a queen. So I think that's always super cool. So you can kind of create a function to do this. And this, to be honest, not very useful for like data science pre-processing, but really useful to know and understand that this is how word embeddings work. So here, if I'm taking a look to see, all right, what is Japan to the Japanese, Australia to Australian? And of course, you have all of these other examples. New Zealand is over there. You have British, Australians, Indian, all of these like nationalities. So it knows roughly what you're trying to talk about. Australia and beer, France to champagne. So really cool that you can do those analogies too. Same, you can do it with proper nouns, Obama to Clinton, Reagan to Nixon, all of these. I don't know too much about American history or not, so, but I assume that that's fairly accurate. Analogies as well, tall, tallest, long, longest, a bunch of examples here. So very, very cool. With word vectors, you can also, there are a bunch of methods that are just there so that you can, do quick methods on word vectors. So one of them doesn't match between England, France, Germany, and Russia. I thought it was pretty funny that it gives you England because of Brexit. I don't know if that's the reason, but that's what it gives you. Cool. So all of these methods, really fun to play with, but what is the value of doing this for data science? So for data science, we're very rarely dealing with singular words. So one thing that you can do is take all of your word vectors for each word. And if you have like a sentence or a document as your data point, you can just turn it into a document vector. That's one way to do it. So let's just say I have this sentence, I like my coffee hot. One thing that you can do is create a list of vectors. And what I'm doing is I'm just appending the word vector for each word into this list of vectors. So with this, except here, I put this try and except just in case a specific word doesn't exist in the word vector library. Once this is done, I end up with an array that represents my entire sentence. So if you want to do the GenSim method for an entire sentence, this is what you can do. One of the downsides of this, because we've added all of our words together, we've aggregated all of their words, this gives us a similar problem as bag of words methods, because again, once we're aggregating everything, it doesn't retain the meaning of the words at all. So because of that, this is not the method that's typically used. However, if you're doing just singular word analysis, GenSim is great. Cool. One last thing for GenSim. I'm displaying a PCA scatter plot over here, and I have a bunch of just random test words. So there's a bunch of random test words. And what I'm doing is I'm just transforming this into 2 dimensions because each of these is 100. Transforming each of these words into 2 dimensions and plotting them on this graph. And these are just like a bunch of random words. And already you can see that it's starting to group the words that should be grouped together. So for example, over here, we have all of the like edible things are up in this corner here. Here we have more like places, like countries. You have institutions, kind of, just places. And then down here, we have all the animals. So it's really cool to see like in 2D, even in a 2D representation from 100 dimensions, you can sort of still see the variation and where these vectors take place. Cool. Any questions about the GenSim library before we move on? I'll tell you with modeling, Spacey is the one that's more commonly used. So we'll get to that and I'll show you all like an actual process. All right. Okay, so again, the library that is more commonly used is Spacey, and I'll tell you that Spacey actually recently underwent this really nice upgrade that has streamlined even more processes. That's really nice. So here, what I'm doing is I'm importing TQDM. And if you haven't come across TQDM yet, I don't use it very often because I find it very buggy. But if you like progress bars, TQDM is a open source Python library that does progress bars, but specifically only for loops. So if you want to see progress bars, you can do that. Anyways, I have my pandas, and because I'm on Google Colab, I'm not sure if I've shown you all this before, but because I'm on Google Colab now, and I have a CSV that I want to read, I can actually mount my Google Colab onto my Google Drive. So I took the CSV that we're going to be using today, threw it in my Google Drive, mounted my notebook onto my drive, and then CD'd into the specific place, and I can read my CSV file. So if anyone wants to work on Google Colab instead of on their local machine, this is what you can do. Anyways, so this is our CSV. I believe this is still the, I want to say this is still the satire data set, but I forget. But anyways, it's some data set with zeros and ones. And this is the raw data. Now, within Spacey, there are actually a few different word embeddings that you can use. So actually, let me show you all where this is. I think I linked it somewhere here. There we go. So within Spacey, there's a bunch of languages that it supports, which is awesome. And then let me grab the embeddings. Okay, so the word embeddings, there are a few different ones that they have. Let me find it. They also recently changed their documentation. I don't remember exactly where it is. Training models. Hold on. Spacey core. There we go. Okay, so for English, there are a few. So there's a small one, there is a medium one, and there's a large one. And I don't know what this one is. This is a new one and doesn't look to have anything either. The only difference between small, medium, and large is that is their dimensions. So the small one has a dimension of, I forget how many. I think it's 96. It says 0, but it shouldn't be 0. I believe it's 96. The medium one has 300 dimensions, and the large one also has 300 dimensions, but is trained on a lot more data, I believe. 20K unique vectors. Here you have 685K unique vectors. Anyways, what you have to do to use Spacey is to first download the word embeddings. And so that's what the cell over here does. So this downloads the specific pre-trained word embeddings. You only need to run this one time. So actually, let me make a note here. Only need to run this once. Cool. So once this is done, all you have to do is load up what embeddings you want to do. And creating the embeddings within Spacey is so streamlined that all you have to do is do a .apply on the raw text. So you can see that I'm running it on raw.body, which is the body of text. .progress apply is what gives me this progress bar, and it took 1.5 minutes, so not too bad. And then I'm just applying NLP, which is so convenient. NLP is the library here. So in this one step, I've created my embeddings. It doesn't look like embeddings, but once you see something that looks like this, and I'll go into this data to show you what this is, the embeddings have already been stored and created and saved. Cool. So let's look into these embeddings more. So first, I'm going to call the first Spacey this whole thing because I want to inspect what this looks like. So I'm calling this first Spacey. Remember, the first Spacey refers to the entire first document. And then I'm looking at the type of first Spacey. It is a document. Cool, as expected. Then I can actually iterate through the first document to look at specific words. And the type of the first word is a token. So there's like kind of levels of information that we can get. So first Spacey, as we know, looks like this. This is our text. First Spacey 0 is our first word. So what can we do? From Spacey's documentation, tokens and documents all have different attributes that you can play around with. So for example, for tokens, you can actually do very similar things like similarity between tokens. You can get like the position. I guess that's not very important for us right now. But yeah, you can see the vector is the most important thing. So we can look at the vector for our first spacey, and it is a vector of length 96 for a spacey. Similar for the document, we can actually get the documents vector. And the way that they create a document vector out of a word vector is not as simple as just aggregating all of the words within the sentence. It's actually taking into account the sequence of words, how the words are used, things like capital letters are taken into account. Punctuation is also taken into account. If you have emojis in spacey, spacey also knows how to read emojis. So that's very, very cool. You actually don't have to do a lot of text pre-processing before taking your data through spacey. So that's something that's really, really neat. Unless there's something that you purposely want to normalize in your data, you pretty much don't have to clean your data before sending it into spacey, which is very, very useful. Cool. So this is our first spacey vector. This is our first document vector, length of 96. These are the numbers. Again, by themselves inherently doesn't mean anything. All right, and this is our token vector. So one of the other things that you can do with spacey is if you wanted to do some sort of analysis on part of speech, you can actually do that. So .pos is part of speech. And you can see that for each word in the document, you can get verb, that's noting. I don't know what that is, but that's that. Determinant is the noun, all of that. So you can get a lot of this information from spacey. Now, how do we get this into modeling? All you have to do is just take all of the word vectors for every document and just stack them on top of each other. And that will be the data frame that you send into your model. So I'm just using the VStack method to take all of my vectors and stick them on top of each other. So I end up with this data frame of 1000 rows because I had 1000 data points and 96 columns because our spacey had 96 dimensions in a vector. So from here, you can just throw this into your train test split, throw it into your model, and the rest of the processes are all the same. Now, some pros and cons to using spacey versus using something like TF-IDF or count vectorizer. First of all, spacey doesn't have much matrix sparsity, right? When we're using count vectorizer and TF-IDF, the number of unique words is the number of columns. And usually our columns are in like the thousands, tens of thousands. I've seen like 100,000 columns when you use TF-IDF without controlling for the max features. So that's one pro of using something like this. You are constrained to the number of columns that the pre-trained vectors have, or the length of the pre-trained vectors. So here we're at 96 columns, which is comparatively not so much compared to like 5,000 columns. One huge downside though of spacey is that none of these features inherently by themselves mean anything. So if you were to look at feature importances will not mean anything. It'll tell you, okay, well, spacey dimension number 5 is the most important. Spacey dimension number 10 is the most important, but that to us is not good for inference. So it is possible that if you're doing an NLP project, you employ both just to see maybe one for prediction. Maybe this gives you better prediction results, but if you want to get information about the separability of your data, you might end up still using something like TF-IDF instead. You also don't have sparsity, so you're saving a lot of space when you have your data in vectors like this. Cool. Any questions about word embeddings?
Yeah, I had two questions. So what if you use medium or large? Would that affect? How would it affect
the models?
Yeah.
Yeah. Okay. So I'll answer that one first, and then we'll to your second question. If you have more dimensions, typically it means that you are embedding more details of your text, because you can represent more things in 300 numbers versus 96 numbers. So using medium or large, you can just have more information that is embedded in these numbers. These numbers, you'll typically see a little bit more variability, but yeah, you'll just get more information from some of the larger data sets.
All right. And you said that with Spacey, it can also take in like emojis, right?
Hmm. Hmm.
Would that does it have the capability to like um interpret the emotions, like the different types? Is that what
Hmm.
it's capable
Yeah, yeah. So that's actually something that's newer to Spacey. I haven't put it in this notebook because I haven't played around with it enough myself. But Spacey also has sentiment analysis. So Spacey sentiment analysis. Let me see. Let me see this one. So in within Spacey, you can also detect emotion. So this is an example. This is not the strongest example, but this goes to show that if you're running the if you're running that NLP command, which is the same thing that I had over here, let's go up to it, this NLP thing. So this is pretty much a pre-processing pipeline to create these word embeddings or document embeddings, both. You can add text blob to it. And I don't think I've talked about text blob yet, but text blob is a sentiment analyzer. So with the text, and something that you can do is grab the polarity, which is how positive or negative it is overall. So you can see that the polarity is overall like a little bit negative 0.125, and it goes from -1 to 1. Also, how subjective is it? That's also something that is included within this same pipeline. It's a 90% subjective statement, because this statement is, I had a horrible day, worst day ever, but every now and then I have a good day that makes me happy. And then if you break it down, if you look at the assessments, they actually show you like, all right, what are the things that they're considering? So you can see here they have punctuation. If you had emojis in this, they would also include the emojis. Like it will also analyze the emojis. So that shows the capability to recognize like tone and the sentiment, emotion.
Okay. All right, thank you.
Yeah, you're welcome. Yeah, Spacey is really, really cool. A lot of these things come from Spacey 3.0, and I was using Spacey 2.0 when it came out. 3.0 has because all of these like additional things like doing sentiment analysis used to be like you have to do a completely separate process, but now it's all done in one. So if you add this, you can actually get these from it. Actually, I'm not sure if it's gonna work out for me great right now, but actually it will take a little bit of time to run. But while we finish up topic modeling, we'll see how it goes. Okay, never mind. Let me quickly pip install it so that hopefully we can try this out to see if it works. Because I think this will be cool to demonstrate. All right. If this doesn't work, then never mind. But let's let this run, and then we'll talk about topic modeling next. Wait, before I move on, any other questions regarding word embeddings? Okay, cool. All right, it broke, so never mind. Okay, so topic modeling is the soft clustering method I was talking about that NLP, that's great for NLP. And topic modeling is great because if you have so much text, it's very hard to do. And when you're doing EDA, it's very hard to do EDA past things like word clouds, word counts. You want to kind of get a sense of what people are talking about in your text. And this can be very, very useful for doing things like market research or doing things like analyzing your text to see what are the main topics of conversation or topics of things that the text is talking about. So the main model that is being used here is actually called LDA, stands for Latent Dirichlet Analysis. And this library that I'm pip installing here is a way to visualize the results of your LDA model. So I'll show you all that process in a bit. So first, I had to download stop words because I didn't have that in my Google Colab. But here, this is actually something that I got from their documentation. So I copied it over. But you're basically using Spacey's word embeddings to process your text so that it can be used for topic modeling. So feel free to take this function. And once you're done, you just have to feed it into an LDA model. And the main thing that you have to do is just tell it how many topics you want to come up with. So basically it's doing the clustering it's going to do the clustering for you. You just have to tell it how many topics you want. Other things that you can do, the more passes and iterations that you do, we'll actually talk about passes and iterations next week when we get to neural networks. But passes and iterations, just how much it's going to train on itself to figure out topics. But this is going to be the main thing that you're going to tweak, the number of topics that you have. So just by itself, without the visualization, when you print the topics, this is what you get. Actually, let me do something a little bit clearer. If I do a for loop for topic in this, let's print topic. All right. So here you can see that we have 4 topics, and these are the words that characterize each of the topics. So it's kind of like a linear combination of words that characterize each topic, which you can actually a lot of times get be able to label your topics based on these. So for example, this first one, cool, it's talking about government, country, election, forest, security, so on and so forth, which is kind of different from call, state, work, so on and so forth. Military, troop, that one seems to be more, I don't know, violent. And then this one's on like migrants, people, women, city. So given that this text seems to be political, you can start to discern what are the main things that are present in this text. However, to make things a little bit easier to interpret, we can use PyLDA-Viz, which is the visualization library. And all you're doing is just feeding in your LDA, your trained LDA model. So use this code and you get this output. So with this output over here, you can see that we have 4 distinct bubbles. Each bubble, basically, the size represents how many or how much of your data set is in each topic. So the most salient topic will be topic 1 that's down here. And these are the words that make up topic 1. So you see we have year, call, state, work, pretty much the same thing that we had in that output over there. But in this format, you can sort of see the comparison between the term frequency within the topic and also term frequency outside the topic. So you can see here, for example, the word say that has this long blue bar means that this topic doesn't have as much occurrence of the word say as other topics do. So here you can see that say for topic 2 takes up a lot more. And so just looking at this, you can sort of get a better sense of what are the main things that people are talking about. Now, sometimes when you're doing LDA, some of these bubbles might like overlap. And that's just that just signifies that you want to change the number of topics that you're throwing into your model. So for example, if I didn't have it like this, or if I had it like, I'm just going to draw something. Let's just say that I had it like, maybe I had a 5th bubble that was like over here. And this was like topic 5. That would signify that, okay, I don't want to do 5 topics. Maybe I lower it down to 4 or perhaps even 3. So that's something that you would tune. And using this PCA graph of the distribution of your topics, that's how you tune your number of clusters. Cool. So this is a really, really useful EDA tool. I think especially if you're doing something like text classification, creating an output per each class to just see what the different things are being talked about within each class. That's really, really cool to see, and it makes for very good EDA. Another use case of LDA is some people use this for feature engineering. So you can actually do dot predict using LDA. So once you have your LDA model, which is this object over here, for LDA model, you can do LDA model dot predict, and then you can actually get the percentage of I guess, where each topic belongs. So let's just say you have row 5 of your data. Row 5 might be 80% topic 1, 15% topic 2, 2% topic, I don't remember what my percentages were, but it'll basically give you like a probability breakdown of what each data point is. And that could be actually some pretty useful feature engineering depending on what you're working on. Cool. So I guess that didn't work up there, so I won't go much more into it. But if anyone's working on Spacey and wants to do that, I will. I know some past projects who have managed to do it, so I can source that for you all. Cool. With that, that's NLP. Again, for your projects, I'm not expecting you all to include word embeddings nor LDA for your phase 4 projects. That's important to note because these are appendix materials. You don't have to incorporate it into your phase 4 projects. However, if it's an NLP capstone, and I feel that it would be a good value add for your project, I would like to see this in your capstones. Cool. With that, anyone have any questions on anything I talked about today? Sweet. All right. Cool. I talked about the project yesterday, so I'm not going to go into more today. Now, next week, we start neural networks, which is going to be 3 study groups in a row of neural network stuff. It's going to be pretty intense. But yeah, neural network in itself, I feel like should be a whole nother bootcamp course, but we're going to go through enough of it so that you'll be able to implement. And I mean, yeah, it's one of the project topics. So you'll be able to implement neural networks hopefully next week. All right.
Is this going to be, is this on our study group notebooks?
Yes. So this notebook is on your study group notebooks. It just for some reason, oh, I know, because on my local machine, I changed the version of Python. So it wasn't running on my Jupyter notebook, but if you look into NLP Advanced, it should run on your local machine fine.
Thank you.
Yeah, so it's over here. Anything else? Cool. All right, if there's nothing else, I will see you all next week for neural networks, and I'll see you all at your respective 101s. All right,
Thank you.
have a good night,
Bye-bye.
everybody.
Good night, everybody.
Thank you.
Good night.
Have a good night, guys.